Okay. We're going to spend 2 days on this. Today, I'm going to teach you how to do it. Tomorrow, we'll simply add a little bit more complexity. No trig today. We'll add some trig tomorrow. That's basically the complexity that we'll add to it. And then we'll move on to the far more important part of the rest of the chapter, which is 3.7, 3.8, 3.9. Why is this not cooking? Okay, homework. Yes, we're going to do 2 problems today in class. And yes, I gave you 5 of these tonight for homework. So it will take us probably not the entire 50 minutes to do the 2 if we were just to start them, but it will certainly take us 10 minutes per problem. So that's roughly 50 minutes worth of homework. Depends upon how fast you are. Good. Okay, a summary of curve sketching, a pretty bad name. It should be called graphing a curve, right? It should be called graphing a curve. They're going to call it summary of a curve because it's going to include, called summary. It's going to include all the previous knowledge we have on sketching curves. So it's going to rely on your knowledge from pre-calculus and then the previous chapter that we did, actually still chapter 3, but I break the chapter down to 2 parts. So it's going to require you to remember what we did on the previous test. All right. Yeah, you're going to graph this by hand. That's the whole trick. It's challenging today simply because of the number of procedures required for this. What's the difference between what we're doing now and what was on the last test?
We did little bits of it.
Did we graph a curve last time?
Not really.
What did we say we did?
Just sketches.
We sketched a curve. And if you notice when I was teaching it, I made the comment a couple times, hey, we didn't really use any calculus when we did the sketch of the curve. We used more pre-calc skills. Well, now we're going to rely on our calc skills, right? So it's an entire section of graphing a function by hand. You should know that my opinion on this is, well, we are in the 21st century. Well, I would absolutely say, why don't we just use our calculator type thing to do this? I will say this, though, in defense of this from our book, it does stress some important things, and it also locks in your head some basic understanding of shapes of curves and its correlation to the calculus behind it. So that part I agree with. I'm just saying spending 10 minutes to graph one curve when I have a graphing calculator sitting next to me seems like somewhat of a waste. But I will agree that some of the skills taught in this procedure allow you to, I don't know, further rationalize or get the geometric picture of what we're doing. All right. From the last chapter test, I asked you to sketch a curve. Yeah? Yeah? And today, I'm not going to ask you to sketch the curve. I'm going to ask you to. What was the big difference of what we didn't include when we sketched that curve? Like on the test, let's see, we established where are the zeros, where does the slope equal 0, and then we just kind of played connect the dots. What did we not do? Which, for instance, what specific other values that we possibly could integrate into this? What possible values in calculus can we now calculate that we haven't been putting into our sketches?
Mean value?
What?
Mean value?
Not really. What have we been calculating? We've been getting pretty good at, but we didn't include in our sketch mins and maxes. We never included. If you remember when I taught this, I was like, hey, we just learned these things about mins and maxes, couldn't we? As you look at this curve right here, does it have a min and a max? Does it look like it has a min and a max? Really? Kind of looks kind of horizontal right here to me, right? turns out that if you were to zoom in, you would find that it actually does have a min and a max. It's just hard to see like here, right? So how can we find the mins and the max? How do we find the mins and the max? Come on, you just took a test on this last week on Thursday. Okay, so we have a test for mins and max, and that test is the second derivative test. We find the first derivative and find the zeros. That's where mins and maxes occur. And what's the second derivative test for?
Which one they are.
Yeah, to figure out which one they are. So the second derivative test doesn't tell us where they occur. It tells us whether they're a min or a max, right? If we zoom into this part right here where it looks like it's horizontal, right? We actually find out there is a min and a max there. Min and max occurs where the first derivative is set equal to 0. Nick, give me the first derivative.
24x squared minus 42x plus 18.
Okay, so we get our first derivative. What are we supposed to do with this, Matt?
Equals 0.
Anything factor out? 6, factor out is 6. Now what? Now we got a factor. All right. First number? First number? What's the first number?
4.
4. So give me the factors.
2.
Or pick one. Pick one. 1 and 4. Last number?
3.
1 and 3. Middle one's got to be negative, so one or both of these have to be negative. Middle number's negative. So does one or both have to be negative? Look at the numbers. If this is 3 times negative 1 is negative 3, not positive 3. So both of them. All right, crisscross. What do we get? So what does it factor to? Sitting right here. There we go. I wrote it backwards than what you said, but yes. Got it? Okay, cool. Now what? Now what?
Zeros are 1 and
1 and 3/4. 1, comma,
4/3.
3/4. Right?
4/3. Not 3/4.
We're divided by 4. Okay. Yes? Everybody good? All right. These are where the mins and maxes occur. How do we find what the min and the max is?
Plug that back into the original.
Into the original function way back up here. We plug that back into the original function and we find out, look, I zoomed in way greatly here, that now you can see that they actually are a min and a max. If I throw 3/4 in, I get 7.06. If I throw 1 in, I get 7. Cool. And notice how much I'm zoomed in. This is just y value 7 right here. And this is x value 1. So we can now see clear that we do in fact have a min and a max. So we can use that technique in order to make our sketches way better. All right. So it turns out that if we combine our knowledge of calculus with our pre-calculus knowledge of how to graph, we can get a much accurate, a far more accurate picture of what the curve should look like. So that's what we're doing today. All right. So in front of you right now are 6 blank boxes. Inside of those 6 blank boxes, we are going to write the steps and the procedures. In fact, it's not 6 blank boxes. It's actually, flip it over. It's actually, no, it is 6. That was 7. So it is 6 blank boxes that we're going to write things. So we're going to combine our knowledge of pre-calculus. We're going to combine our knowledge of calculus to get the complete and total pictures. So that's why today's class is called graphing and not sketching. Okay. Make sense? All right. How long is it going to take to do one problem?
10 minutes.
10 minutes. Right. So I'm going to take this medium task of sketching and turn it into a far more challenging task called graphing. Right. So for those of you that are cool with, 7, 18, 20 steps, you'll be fine. For those of you like 20 steps to get to one answer, that's a lot. Well, then that's why this is much more challenging of a task. We've done basic sketching. Now we're gonna do that accurate sketching called graphing. All right, in the first box, we're gonna write down the 8 steps. So these are the things that we are going to consider when we're actually doing this graphing. And if this bothers you, well, then here's someone of a like mind looking at you. This poor little girl for the rest of her life will have to go to PowerPoint presentations and see her face as representative of whatever the emotion you're trying to convey that she's conveying right now. I'm trying to convey like, man, this is lots of procedures to do here. We're going to calculate the domain. We're going to find the intercepts. We're going to determine symmetry. We're going to find the asymptotes. We're going to find whether it's increasing, decreasing, or where it is. We're going to find those mins and max. We're going to find the concavity. We're going to find the inflection points before we actually do our sketching. If this sounds somewhat familiar, with the exception of increasing and with the exception of mins and maxes, the rest of the stuff we all did in pre-calc. However, when we did it in pre-calc, we had a different technique because we didn't know calculus to do some of those. So some of these we're going to accomplish using calculus procedures. Others of them we're going to rely on the tried and true pre-calculus methods. So we're going to find 8 things before we attempt to do our graph. By the way, the book still calls it sketching. I'm the one making the distinction between a sketch and a graph. All right, you got them all written down? Ready to go? All right. So we'll explain the key parts here in detail. Ready? All right, how do we find domain? This will be box 2. How do we find domain, Matt? How do we find the domain? Nick, you remember how to find domains?
No.
Abby?
There isn't like anything except if it has like asymptote.
There are 2 things that give us problems that we encounter. There are more. The 2 main ones. The 2 main ones that give us problem for domain are, where do they occur?
What?
She said asymptotes. He said holes, and all I said was, where do they occur? How do you find that out?
In the denominator.
In the denominator. It's not that you have a denominator, it's that you have a denominator with a variable. If its denominator is 3, there's no hole, there's no asymptote. So yeah, so key problem area number 1 is when we have a denominator and we have variables. Key problem number 2. Where's the other thing that gives us problems?
Jumps.
What?
Jumps.
Yeah, I mean, that's true. We're not going to have anything that's piecewise. Key problem area number 2. In math in general, what gives us problems? Well, that gives lots of people problem, but that's not the problem I'm thinking of. Denominators are variables, and what gives you error on your calculator when you type it in? That's the denominator. That's literally why you get that error. You're dividing by 0. That's where your x value produces a 0. What?
Circles.
But non-functions, we're only going to be dealing with functions. How about square roots? Try to take the square root of a negative number. Your calculator says error, right? So I guess you need to write these down. The domain is where the function is defined, except we usually don't make this as our definition of domain. We say it the other way around. What would be the other way around? Say this backwards.
Defined as function.
Mathematically.
Where the function is defined as the domain.
That is, but I'm saying, what's the opposite of this? Because that's usually how we think about domain. We don't usually say the domain is all real numbers, although occasionally we'll say that. We usually say the domain is
All numbers
except part. So usually we say what values are excluded. We say that's our domain. So typically we put this in the form of, well, what numbers can you not be? You can be all numbers except for 4. So all real numbers except for 4. So that's typically how we write our domains. All right. And then we said there were 2 main areas. the key area is area number 1. You got variables in the denominators. You got to figure out what x can't be. And problem area number 2, even indices radicals. That means square root, 4th root, 6th root, 8th root. It's got to be an even number. The cube root is fine. You can take the cube root of a negative number. You can take the cube root of 0. You can take the cube root of a positive number. But for even indices, that means square root, 4th root, 6th root, they give us problems. There's a third one. We won't see it today. We'll see it tomorrow. And that is where you have a trig function, not sine, cosine, no problem there, but the ones that have vertical asymptotes. Technically, there's no denominator with a variable with tangent, except really there is. Remember, tangent's opposite over adjacent. That's when the adjacent is equal to 0 that we run into problems. And so tan, cosecant, and secant, those are those inverse trig functions, or sorry, those are those functions along with the inverse trig functions that produce vertical asymptotes. What word?
Even in indices?
Indices. An indice, remember, is your index. So what's the plural of index? Index says doesn't sound right. Cool. All right. I'm going to exclude this bottom one for today. We'll pick that one up tomorrow. But we will do the key areas where variables in the denominators and when you have a square root or a 4th root or 6th root, something like that. Okay. Next box, intercepts. How do we find the intercepts, Matt? Which one for which? You got it. Oops, this was supposed to be box 2B. I should have looked. I also didn't break your boxes up, so my apologies. Cool? Hey, this can sometimes be very challenging. Why? Why could this be challenging? When you set your x equal to 0, is that ever challenging? No, it's when you set your y equal to 0 that can be challenging because you're basically asking to solve. So what if it's x to the 5th, blah, 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 big long polynomial, and you got to solve that? Well, then that can be very challenging to solve. So our book, believe it or not, says the following. It says it can be omitted if it's too challenging. Well, I'm just going to say it's always too challenging, right? So use some common sense. If it's a quadratic or something like that, you can solve it. But if it's something to the 5th power, right, you can't factor anything out, then that's a bit too challenging to solve. Okay? You might want to graph it and just have your graphing calculator tell you where the zeros are or the intercepts are. Okay. All right, this is supposed to be box 3. This is supposed to be box 3. All right, remember how to calculate symmetry? This is from pre-calc. We had y-axis symmetry, we had origin symmetry, we had x-axis symmetry. Remember how to do that? Do you remember doing it? Okay, so let's just write it down since you're most people. The 3 types of symmetry we will be looking for is y-axis symmetry. That means it can be rotated about the y-axis. This is the one where you plug in negative x and nothing happens. Remember doing that? You plug in negative x, you simplify, you get back to the same function you started with. That means you have y-axis symmetry. We also called it for even functions. We said that if that's the case, then it's even. We're more interested in the fact that it is y-axis symmetry. We throw those words even and odd because remember when we get to the trig functions, right? Sine, cosine, tangent, OEO, odd, even, odd. For origin symmetry, that's when we throw negative x. And when we factor out a -1, it turns back into the original function. Remember doing that? You plug in negative x and then you factor out a -1, that's the negative f of x. If it turns back into a -1 times the original function, then it has origin symmetry. That means it's been rotated around the origin. And then for the last one, because we'll be dealing with trig, those are called period. Remember periodicity? Remember that fancy word? So if something just repeats itself over a certain period, we say it's a periodic function. So for instance, sine repeats itself every 2 pi. So if it can be written as f of x plus a period, and that gets you back to your original function every single 2 pi, sine looks exactly the same way, then we say that function repeats itself or is a periodic function. Those are the types of symmetry. And the last one, it's going to be primarily, it's going to be the trig functions. All right, so that's all supposed to be in box 3. Good? All right, let's go to box 4. So box 4 is the asymptotes. You guys should know how to do this. How do we find the asymptotes? How do we find the asymptotes? So we go to the bottom, right, to find which ones? Vertical asymptotes. Vertical asymptotes are found from the denominator. Where are horizontal asymptotes found? You better know this one. Or I shouldn't say where. How are the horizontal asymptotes found? Take the limit as x goes to infinity and to negative infinity. Okay, so we take the limits at infinity. Hey, that's a new technique. That's not what we did last year in pre-calc. This is our new technique. You said the vertical asymptotes come from the denominator. It says do this after you factor and cancel. Anything that cancels out is a whole. That's part of your exemptions from the domain. Remember, when we find the domain, we don't cancel anything. We can still factor, but we don't cancel anything. Wait, it says 3 types. What are we missing? What are we missing? The diagonal or the oblique ones, right? We will not see that today. This is still an open-ended question that I asked you, and even last chapter we were talking about vertical and horizontal asymptotes. I said, remember how to calculate diagonal ones? Nobody remembered. And I said, well, we will revisit it. So we will revisit it, not today though. Okay, so more to follow on oblique or diagonal asymptotes. All right, now we're going to get back to the more box 5A. We'll be back to the ones that we kind of know off the top of our head. Well, at least I think we do. Let's see. Everybody good? All right. So 5A, remember how to calculate increasing, decreasing? What you do? Step 1. Step 1. I want to find increasing, decreasing. Step 1. And you guys are going to need an awful good resource card for semester final. Because you literally had this last test.
I'm trying to think.
Take the first derivative, then, okay, that's going to tell you your critical points. Then take the second derivative.
Zeros for the in where are they
Do
called?
you remember doing this? We take the first derivative, we find those critical points, then what do?
Put stuff around.
Put stuff around it, right? And find out whether it's positive or negative, right? Where it's positive means,
Increasing.
and where it's negative means it's decreasing on those locations. That's on the first derivative. I said second, I meant first derivative. I was thinking about the next one. So this is box 5A. So what's 5B going to do? No, that's increasing and decreasing. What's 5B?
Oh, mins and max.
Mins and maxes. Okay. I'm gonna make a slight change. Make a slight change. Okay. Local mins and max, we know we got to find that critical point where the slope is equal to 0 on the original function. That's the first derivative. Find the first derivative set equal to 0. Those finds us the locations of where mins and maxes occur. In the previous chapter, don't write this down. In the previous chapter, it said to find whether it's a min or max, you take the second derivative and you apply the second derivative test. Yes? What was the previous thing we just calculated? If you already know where it increases or decreasing, you don't need the second derivative. You can get this information simply by looking at where it increases or decreases. Let me explain that, right? Yes, this method will work right here perfectly fine. If you're just looking for mins and max, that's what you should do. But if you've already calculated where it increases or decreasing, you simply look at that, all right? If this is a min and this is a max, yes? What happens to the left of a min?
Decreasing.
What happens to the right of a min?
Increasing.
And the previous step, you just found out where it increases or decreases in relationship to where y prime is equal to 0. So you're already going to know that whether it increases or decreases. And then on a max, it should.
Increase, decrease.
Does that make sense? And the only reason we're not taking the second derivative is because on the previous step, we found out where it increases or decreasing. So I don't want to do any extra work if I don't have to. If you forget all that and you're like, local mins and max, I do the second derivative. If it's less than 0, it's a max. If it's greater than 0, it's a min. Then by all means, enjoy. I'm going to use this technique right here because I just, the previous step, calculated increasing, decreasing regions. Okay. Concavity, we're almost done. 6A. Last open box. Concavity, what was the concavity test? First or second derivative? Second derivative, right? Where it's greater than 0, it's concave up. And where it's less than 0, that's concave down. Okay, have we done a problem yet? It's just a setup. All of this is required to get the one problem done. Cool. Last thing is, that's what happens between a concave up and a concave down or vice versa. Inflection test, once again, it's the double derivative set equal to 0. That's going to tell you where the inflection point occurs. Remember, it is possible that nothing equals 0. Meaning if it's only concave up, you're not going to get any inflection points. If it's only concave down, you're not going to get an inflection point. All right, feeling overwhelmed yet? Yeah, you should be, right? So if you think that this isn't that bad, you're not thinking through the problem, right? It's bad. It is bad. Anybody movie? It's right. Okay. So for the rest of the day, we're only going to do 2 problems, and we got, I don't know, 20 minutes left. It's going to take us 10 minutes per problem to get them done. All right, 2 examples. All right, so here are my 8 things I need to do. We're going to do one thing at a time. You see the function? Doesn't it look pretty straightforward and easy? Doesn't look that complicated. It just said 2x squared over x squared minus 1. Turns out it's going to take us 10 minutes to get this done. All right, everybody's going to get a step or 2. Matt, you start us off. What's the first thing we do? How do we find domain? We got variables and denominators. We got any square roots? Do we have any trig? So it's just the denominator. What are we supposed to do? And solve. Go. Which is? Which is not 1. Plus or minus 1. So our domain is everything except for -1 and +1. Look how I wrote it though. negative infinity to negative 1, and then negative 1 to 1, and then 1 to infinity. You can write it with either with words, or you can write it like this. Cool? All right, Abby, you're up next. What are we finding? How do we find the intercepts?
Set y,
Do the easy one first.
okay, y-intercept set x equals.
So to find the y-intercept, we set x equal to 0. Oh, I did it. You were right the first time. I thought I did the easy one first. I usually do the easy one first. All right, x-intercept, set the y equal to 0, solve. Ooh, look at it. It's ugly, except
Just focus on the top,
why just what happened to the bottom?
because you don't need anything on the top that's 0 will make the entire thing 0.
Okay, I like that logic. How about we rephrase this and frame it in the sense of I'm solving an equation? What would be the first step?
Top,
What would be the first step if I'm solving this equation?
but multiply.
Both sides by the denominator, which would make the denominator go away. Not that your point wasn't valid, it's just that you also need to make sure you understand the algebra behind it. Okay, so therefore x is equal to
0.
Well, that was easy. Looked like it was going to be challenging, but this one was okay. Now to find the y-intercept,
Set the x's equal 0.
and clearly that's going to turn into
0,
0. So what are the intercepts?
0, 0.
In other words, just the origin, right? Make sense? Okay. Nick, what are you doing?
Symmetry.
Symmetry, what are the steps? There's only one step.
Like the negative part,
Everywhere you see an X,
but negative.
put a negative X. So I take the original function, and anywhere I see an X, I'm going to put parentheses negative X. Okay? Now what?
Just like the negative x.
Simplify.
Yeah.
Okay, so
It just goes back to the same.
just go, well, parentheses negative X squared is X squared. Does this look like what we started with?
Yeah.
So therefore you can conclude that it has,
Uh,
you wrote it in box, whatever.
periodics.
This is not periodic, no.
Or just a origin.
If it looks like what you started with when you plugged in negative X,
Then it's
then it has
one x.
y-axis symmetry. When would it have origin symmetry?
When it's both.
If I were to factor out a -1 from the answer, I'm still going to plug in negative X, but if I were to factor out a -1 and then it turned back into the original function, then it would have origin symmetry. Periodic symmetry is when we're going to have a trig function. Okay. All right, we're back to Matt. What are you doing? Matt, they're up here. But yes, they should be on box 1, 2 of your paper. Did we found asymptotes? Yes or no? We have not. How do we find the asymptotes? Okay. Solve for the denominator. Oh yeah, factors, see if anything cancels. Anything cancel? Nope. So, and we already did this, remember? We found this. So the asymptote one, if it looks like this, is a pretty quick process, but I'll say it doesn't really say that up here for the domain because the way we wrote it. So maybe you would have to repeat the process. So the vertical asymptotes happen at
-1.
-1, +1. Okay, set equal to 0 and solve. How about the horizontal asymptotes? Got to take the limit. Okay, you just had a test on this. What do we do? So I'm going to divide everything by the highest power of the variable in the denominator. That's x squared. So I wind up with that. Then we take the limit. Okay, limit of 2 is 2, the limit of 1 is 1, the limit of 1 over x squared is 0, so that turns into 2. Now that's the limit on the right. Now we have to, no, this is the limit on the right at infinity. Now we got to look at it on the other side. So what's going to change? What's going to literally change?
Nothing.
Well, the infinity is going to change to negative infinity. I'll write this, but the reality is nothing really changes until we get to the last step when we're throwing in negative infinity. But when we throw in negative infinity, nothing changes. We're still going to get 0 for 1 over x squared. Technically, we're going to get 1 over negative infinity squared, right? But that still gives us 0, so we'll get 2. Does that mean we have 1 or 2 horizontal asymptotes? Depends how way you want to think about it. We definitely have one on the left and one on the right and one on the left, but they're both the same value. Remember, in the middle, the function, though, can go through that horizontal asymptote. Okay, so we have 2 horizontal asymptotes, but they're both at the same value. Y is equal to 2. Cool? All right. Abby, what are you doing?
Increase.
Increase and decrease. And how do we find that?
Well. Find the first derivative.
First derivative. Okay, what's the problem with this one?
You have to do that.
Never done this in a while. Okay. Quotient rule. Well done. All right, quotient rule, low D high minus high D low over low squared.
Yeah.
So low is
2x.
low is low D high over high D low. I'm sorry, low D high minus high D low. There, I said it correctly. What's on the low?
X squared minus 1.
Derivative of the high. Okay. Minus high.
2x.
Derivative of the low. Two x. The first one, when I said high, you should have said 2x squared. I didn't
Okay,
correct you on
well, I
that.
was doing the
All over. Okay, squared. Okay. All right. So first derivative, this is what she said. Notice I moved the 4x to the front and the 2x to the front, but same idea. Okay, what do you want to do now, Abby? Don't overthink it. What do you want to do? Just let's do some math.
right
What math is up there?
distributive.
Let's distribute a property on both of them. So we would get
4x cubed minus 4x minus 4x cubed.
okay. And the bottom, I guess we could square if we wanted to. I don't think you've ever seen me squaring the bottom ever on a quotient rule. Hey, what do you notice?
Negative 4x.
So what are you left with?
That.
And that's your first derivative. Except we're trying to find increase and decrease. So what do we do with this?
That equals 0.
Okay, so we solve it. Okay. Stop panicking and just look at it.
This is 0.
It's just 0 because we multiply both sides by the denominator. We get that, and that's 0. So this is our critical number. What do we do with that number? Put it on a number line and then pick.
-1.
Why am I groaning?
Is it weird?
Why is my green dot right there? I can't choose -1 or +1.
Okay, -2,
Right.
+2.
So what would have happened if you choose -1 and 1? When you plug it into your calculator, what's going to happen?
Error.
You're going to get an error, right? Okay. And then you're like, why am I getting an error? And you're going to think you typed it in wrong. And then you're not even noticing that you picked a number that's not in the domain. Okay. So we plug those numbers back into here. and we see if we get positive or negative. For the sake of time, you want me to show you the answer? Okay, so on the left side, you get a positive number, on the right side, you get a negative number. But all we're doing is just throwing -2 and +2 into this and seeing if we get a positive number or a negative number. Yes? Okay, so what does this mean?
Increase.
From
90.
to,
0.
technically not to 0 because we can't go through -1, right? So technically, I'm just going to write it in the larger thing. So you're going to be positive, right? You're going to get a positive value excluding -1, and then you're going to be a negative when you are excluding +1, right? You could also write this in interval notation if you'd like to. I chose to write it like this, right? So I'm increasing from -infinity to -1, and from -1 to 0. 0 is the critical number. And then I'm decreasing from 0 to 1, excluding 1, and then from 1 to infinity. Yes? That makes sense? Are we done yet? We're just a little bit over halfway, right? We haven't graphed anything yet. Why do I feel like we're only going to get one example in this class? Okay. All right, Nick, you're up. What are you doing? Ooh, comfortable territory. What do we do?
Can you just look at the increasing and decreasing?
Yeah, we can go back to increasing, decreasing, because look, we found y prime was equal to the critical number of, so that's a min or a max. We just don't know what it is. We just got to figure out whether 0 is a min or a max. And I said, rather than doing the double derivative test, what are we going to do?
Just do the first.
We're going to look at this and make sense of it. It says increasing 0. This is where the slope of the tangent line is equal to 0. So I got increasing, I've got the slope of 0, and then I go decreasing. So what is it, a min or a max? Think about it. If you're increasing and then you're decreasing, are you a min or a max? I am a max, right? I have to be a max. Yes, you could set this equal to 0 and solve. We still get the same thing, but then we're thinking about this. And we found on the previous one, you're increasing and then you're decreasing at 0. Therefore, it's got to be a max. Did that make sense? Okay. All right, we're back to Matt. What are you doing? How do we find concavity?
Y double prime.
Okay, so we found y single prime before is this. So now we have to, no, another quotient rule. And the bottom, we could, if we could multiply this out, or you could treat this as chain rule. You don't say yes because I said chain rule. Chain, do you understand? Do you see this as being a chain rule? Okay. Okay, cool. All right. So low to high. So low is squared, derivative of the top minus high. And now we got to take the derivative of the low. All right. So derivative of the low is the one we'll write out real quick. All right. So derivative of the outside with the inside left alone.
Yeah.
Therefore, we get
4x.
all over the low squared. Okay. So there's our, what we just wrote, 2 times 2x times that. Where'd the minus 4x? Because remember that was the minus high to low, right? All right. So we're gonna put all that together. What do you want to do, Matt? Well, notice every single term has got an x squared minus 1. Every single term, this term, this term, this term has an x squared minus 1. So couldn't we, well, how many can we cancel out?
1.
Only 1 out of every one. So we're going to cancel 1 out of every one. I just didn't do that. What did I do? I didn't do anything on that step. What the heck did I write that again for? I literally didn't do anything in that step. That's weird. There we go.
And we did.
Here's what I did was I probably shouldn't have written this one. What I said was I'm gonna out of the top, I'm gonna factor out an x squared minus 1. And then I'm gonna cancel. Okay. So if I factor out an x squared minus 1 and then I cancel, then I'm left with that. Okay. Cool. What are we supposed to do with that for concavity?
Equals you.
Okay. And then find out where it's positive or negative, right?
Yeah.
Okay. Well, let's think this through. The top is ever going to be negative? Is the top ever going to be negative, no matter what number you throw in? No, it can't be negative. So the only thing that could be negative is the bottom. The bottom would turn the top with the whole fraction negative, right? If the bottom's negative. So what would turn the bottom negative? Sure.
Or wait, yeah.
0.
0 would make it negative. Well, 0 is a critical number. What else would turn it negative? 1 would turn it into a 0 and it's not in the domain.
Nothing else.
Oh, no, there's more. What about 0.5? 0.5 minus 1 is negative. Negative cubed is still negative. So that would turn it. So
Anything between 1 and 0.
between -1 and 1. Right? In other words, the top is always going to be positive, right? As long as I plug in a number, right? The absolute value is bigger than 1, it will always give me a positive number at the bottom. But if the opposite is true, if I plug in a number between -1 and 1, right? If I plug in a 0.5, that's negative. If I plug in a negative point, whatever, that's also going to make it negative as well, too. So what's going to turn it negative? Any number between -1 and +1. That's going to turn it negative.
Just concave down.
Okay. But it's concave up as well over here, but it's concave down for this one. Does that make sense? Okay. This means that if it's larger than the value of 1, absolute value, okay, -5. -5 squared is 25. 25 minus 1 is 24. 24 cubed is positive, right? So we're going to be concave up as long as we are absolute value-wise bigger than 1. But if we're between -1 and 1, then that's what gives us concave down. Does that make sense? Okay. We're now 15 minutes into this problem, not 10 minutes. Have we completed all the steps? We haven't done inflection. How do we find inflection points? We set this, the second derivative, equal to 0 and solve. All right, do that real quick. Why is that one easier? We accept this is the second derivative.
Oh.
Therefore, think it through. What do? I got a fraction. I got a denominator. What's always the first step? No, multiply both sides by the denominator. That gets rid of my denominator. And we do that because look, what's on the other side? 0. So you're simply left with that. Therefore, what's the answer? You got, come on, guy, you can think this through.
Plus or minus 1/3.
Absolutely not. What would be the first step? We're back in algebra 1. What would be the first step? Well, that would make it negative. And even if I divide by 12, it's still, say it louder, negative. And then the last step is to, and what's the problem with that?
It's a negative square.
So what is this telling you?
Plus or minus.
No. If you get an error for this, that means it doesn't ever equal 0, which tells you
Is the inflection
There's no inflection.
there's no inflection point. Good Lord. There is no inflection point, which means it's either constantly increasing or decreasing. That sounds weird because we found both concave up, concave down, and increasing and decreasing. So something must be weird inside of our shape. Let's see what it looks like. Now we're going to take all of this information. We're going to do our final graph. How should I start? Well, literally, how would I start?
Make a graph.
Make a graph. Okay, I'm making my graph. Now what? Where are the intercepts? It's just one dot. Now what? Unfortunately, it says symmetry next. Symmetry should probably move to the end, but in terms of figuring things out, symmetry should be somewhere at the start.
In the asymptote.
Let's put in the asymptotes. Where are the asymptotes? And two. Horizontal at 2, vertical at -1, +1. Yes? Okay, now what? Literally, what's the next thing it says? We just did asymptotes. What's the next thing? Increasing or decreasing. So if we start at negative infinity over here, what's happening? What does it say? It's increasing. That means if I go here, I'm supposed to go in an upward direction, right? Okay. The problem is it also has a horizontal asymptote, which means it must, somewhere at negative infinity,
Be straight.
must be straight at the value 2. Yes? Okay, so you have two options, Nick. You can either put the curve above the dotted line or below the dotted line. Which way should it be?
Below.
If we're below, the function does what? Increases or decreases?
Oh, wait, no, it's supposed to increase.
So it would have to be above, so it must look like that. Let's finish this. Okay, what's the next point of increasing, decreasing?
Do the same on the others.
What's the next point of increasing, decreasing? So -1 is here, and we're supposed to increase to where? Well, that's this red dot right here. And then it's supposed to decrease. And then on the other side, he said it's supposed to be symmetrical. We could flip it like this, or we can get it from the fact that it decreases from 1 to infinity. And if I decrease from 1 to infinity, it looks like that.
Boom. Great job.
That was 50 minutes to do
One problem.
one problem. For Ish, the rest of you guys can go. For Ish, since they didn't get this one, I'm not going to say anything. I'm just going to go through the next couple slides. So at your own pace, you could review this. Okay. By the way, there's the actual graph, and we got a near perfect copy of it. All right. Yes, sir. Head hurts. All right. So Ish, once again, I'm just going to flip through these really quickly. Through the power of your video, you can hit pause and rewind and kind of tease out where I'm getting this information from. This is a very challenging one to do the first derivative on it. It is quotient rule and then with the chain rule in the denominator. This says that the domain does not include any number smaller than -1, and -4/3 is smaller than -1. So the only asymptote we have is at 0. Second derivative is another huge challenge to do this. This is where the complexity all comes from. So we set that equal to 0, or we say where is it positive, where it's negative. Top will always be positive. So it's where does the bottom turn negative? Any value greater than -1 would turn it negative, or positive, sorry. And then any value less than -1 would turn it negative. And since -1 and less is not in our domain, right, then therefore it is only concave up. The inflection points, right, where equal to 0. You look at our concavity, it's only concave up. So therefore, if it's only concave up, it has no inflection points. I don't need to set it equal to 0 and solve. Take all that information, plug the intercepts, the vertical asymptotes, the fact that it is only concave up, and it is increasing from 0 to infinity, and it's decreasing from -1 to 0, then that's the only shape that you can get. There you go. And there's the actual graph of it. We were pretty darn close. There you go. This is computationally one of the more challenging stepwise, and all these problems will take you multiple minutes, 10 to 15 minutes per problem. I will see you in class. Hope you feel better.